Hi. So, what are we doing here? We're studying vectors in three-dimensional space, right? So last time we talked about what vectors are and what we can do with them. So what can we do with vectors? We can take the sum of two vectors. We get another vector. It is on. Let's see. Let me see if I can adjust it. Is that better? No? What is it about microphones in this class? By the way, I did find batteries after I finished my last lecture. They were hidden in the cabinet. So don't make me do this. You don't want that. Let's see. Like this? Better? Yes. Okay. But tell me if you lose me. If I lose battery. So. All right. Yes, we can take the sum of two vectors, and that's a vector. Or we can multiply a vector by a number. That's a vector. But in addition, there are also more sophisticated operations we can do on vectors. For example, dot product. Now, a dot product is a whole different deal because the input of a dot product is two different vectors, but the output is a number. The output is a number. And I explained last time that there are two ways to define the dot product of two vectors. The first way is geometric. We talk about the magnitudes of the two vectors and the cosine of the angle between them. Which we call theta. So it's just the product of these three numbers. But there is also a second way, which is very convenient in calculations, which is defined in terms of the components of the vectors. And those components will be called x, y, and z. So I put index 1 for the first three components and index 2 for the components of the second vector. So the formula looks like this. Now, we can play with these formulas, and we can derive useful information about vectors by using the fact that both formulas give us the same answer. Okay? For example, we can find the angle theta, the angle between the two vectors, by combining these two formulas. From the first formula, we learn that the cosine of this angle is equal to the dot product divided by the magnitudes. And now we use the second formula. So this is the first formula. And now we use the second one to write this in the second form, xy, x1, x2 plus y1, y2 plus z1, z2, divided by the lengths. But the lengths can also be found from the components. For example, the length of the first one is given by this expression. And likewise for the length of the second expression. So we can write this also very explicitly using the components, or coordinates, if you will. So you see, this is an unexpected formula in the following sense. You have two vectors, and which are given by these coordinates x1, x2, x1, y1, z1, and x2, y2, z2. When we just look at these coordinates, we don't know where exactly the vectors are. We'd have to plot them in space to really understand their relative position. So it looks like it would be very difficult to find out what the angle is between them. But in fact, there is a very explicit formula which uses nothing but the expression for A and B in terms of components. Right? So this formula only uses x1, y1, z1, which are the components of A, and x2, y2, and z2, which are the components of B. And a priori, there's no reason to believe that there would be such a formula. But we were able to derive it by combining two different definitions of the dot product. It's not like it's very simple, but it's not too complicated either. I mean, it involves some square roots and so on, but it is very explicit. So, for example, you can program it on your computer, and then every time so your computer would be, your program on the computer would be like that black box, the dot product, for example. So you can program your computer to calculate the dot product, you get a number. But you can also program your computer to calculate the cosine of the angle by simply calculating this. And that's very simple, which can be done very quickly. So that's the power of these methods that we are talking about. That using these methods, we can learn a lot about the geometry of vectors, say, or other geometric objects, by using as input algebraic information, such as the components of these vectors with respect to the x, y, z coordinate system. One application of this is the following. There is a very special angle for which, special angle theta, for which the cosine is equal to 0. So cosine theta is equal to 0 if theta is equal to pi over 2. Or actually, not just one, but two different values, pi over 2 and negative pi over 2. Right? Right, so if you have an angle like this or like this, the projection onto the x-plane, which is the cosine, is equal to 0. So in this case, the dot product formula tells us that the dot product is 0 in this case. So we can use it, you can use this formula to determine whether the vectors A and B are perpendicular to each other or not. When I say perpendicular, I mean that the angle between them is 90 degrees. But to say that the angle between them is 90 degrees, well, it means that they are either like this or like this. Right? It doesn't matter. In both cases, they are perpendicular. And in this case, A dot B is equal to 0. So if you are given two vectors, it's very easy to find out if they are perpendicular or not. You simply take the dot product given by this very simple formula, number 2, and you see whether if it's 0, they are perpendicular. If it's non-zero, they are not. So that's a useful application of all this formalism. There is one more operation that we will need for vectors, and that's called a cross product. Now, the terminology here is really not very, doesn't really make much, how should I say? It's not very imaginative in some ways. It's just that in the first case, we denote it by a dot, so we call it dot product. In the second case, we use it denoted by a cross, so it's called cross product. There is no underlying reason for calling them this way. It's just a tradition. So don't try to read too much into this terminology. It's just the way it is, because of the kind of notation that historically people have gotten used to over the years. So the second operation is a cross product. And again, I would like to think of it as a black box. Which has certain input and certain output. Okay? But now the input will be the same as in the case of a dot product. The input will consist of two vectors. So there will be vector number 1 and vector number 2. But the output will be, instead of a number, in the case of a dot product, a vector itself. A vector as well. So the notation for this is A cross B. And again, there are two different definitions, just as in the case of a dot product. The first definition being geometric, and the second definition being algebraic. So what's the first definition? The first definition, to explain the first definition, I have to draw a picture. So here I have two vectors A and B. And we should think that they don't necessarily lie on this plane, but in fact, there is some plane which might be sticking out. So I want to draw, I would like to imagine this piece of this plane, which is kind of floating somewhere. It's not inside the blackboard, but it's sticking out. In fact, I can use this blackboard to kind of illustrate it. Yeah? So that's the kind of plane I'm talking about, right? So in fact, I might use it. I never thought of that before. It's a very nice three-dimensional visual aid here. So here is so it gives me a lot of flexibility. In fact, it gives me, I can do all possible planes by, turning it a little bit and then rotating. So, no, really, I'm amused by this. Okay, it's nice to have good surprises. Okay, so here are the two vectors. So now I don't have to explain to you, okay, it's sticking out and so on, because now you can see it. So here's A and here's B. Now, and that's the plane which contains them. So the result of the cross product of these two vectors is going to be a vector which will be perpendicular to this plane. Here I need a big stick, which I don't have, but I have a small stick. I have this. I have my pen. Okay? So it's going to be the eraser. Okay. Thank you. So I'm doing really well in the visual aids today. I'm very proud. So with your help, thank you. So to people watching, this is how it's done. This is a cross product of A and B. Now, so it's a vector which is perpendicular to this plane, which is good because I give you the direction of the vector. Actually, not exactly, because if I just say that it is perpendicular, there are two possibilities for it. It could go like this, or it could go like this. But that's where I use the corkscrew rule, right? And the corkscrew rule tells me that it should, I use the corkscrew rule in the following way, that this vector, and this vector should form the oriented system, coordinate system. In other words, if I turn my corkscrew from A to B, it should move in the direction of this vector. So which means this is a correct position, not like this, okay? So I explained to you what the direction of this vector is, but it's not enough. To define a vector, I have to tell you what the direction is, and I have to tell you what the magnitude is. So the magnitude of this vector is going to be the area of this parallelogram. So in words, the cross product is the vector perpendicular, and I will say the word oriented, where oriented means that A, B, and this vector form satisfy the corkscrew rule or the right-hand rule, whatever you like. And this is a vector perpendicular. I can erase this now because I have a much better illustration. Perpendicular to the plane I will say plane spanned by A and B. Spanned by A and B, it means a plane which contains both of them. It is, in fact, a unique plane. Unless, of course, these two vectors are proportional to each other. If the two vectors are proportional to each other, the answer is going to be a zero vector. So let me assume that they are not proportional to each other like this, so they are not pointing in the same direction. Then they do span a plane. There is a unique plane which contains them. Let me qualify this. There is a unique plane which contains them as soon as I specify a particular point. In other words, as soon as I say to which point I'm applying these two vectors. As I explained to you last time, a vector representation of a vector is not unique. In fact, I could parallel transform it. So I could apply it to a different point, which would simply mean moving this blackboard. I'm not going to do this. Now, it's perpendicular to the plane spanned by A and B. And by a plane spanned by A and B, I mean what I just explained, of magnitude equal to the area of the parallelogram, which is spanned by, which is drawn here. I'm not going to write it in words, just to save time. Okay? So what is this area? We can find it very easily because we know that the area of a parallelogram can be computed by dropping a perpendicular line like this. So this is 90 degrees. So let's call this H. And so this area is A, the length of A times H. Right? I have to be careful not to shift it. You know what I mean. A times H. But H, in turn, is the length of B times the sine of this angle right here, which I call, again, theta, because that's the angle between A and B, right? Because you got here a triangle for which this is 90 degrees. So you can find this side by taking this side, which is the length of B, and multiplying by the sine of this angle. So H is this, and therefore the length of A cross B is the length of A times H, which is length of A times the length of B times the sine of this angle. So to repeat, the cross product of two vectors is a vector perpendicular to the plane spanned by these two vectors, which satisfies the orientation rule with respect to those two vectors, and whose length is equal to the length of A, length of B, times the sine of the angle between them. This is the analog of the first definition of the dot product, which also involves nothing but the length and the cosine of the angle. In this case, there is a little more because I also specify a particular direction, which is determined by the plane. Now, what about the second definition? In the second definition, I'm only allowed to use the components xy, y1, x1, y1, z1 of the first vector, and x2, y2, and z2 of the second vector. Right? So a priori, it's not clear what the formula should be. So I'll just give you the answer. And then it's an interesting problem, which you can read about in the book, to see that indeed the two definitions are equivalent. Last time, I explained to you how to show that one definition implies the other. I did not explain how the first implies the second, which you can also read in the book. So the second definition is the following. It involves a certain a new piece of notation. which is called the determinant. The determinant is given by a certain formula. The determinant, you apply the determinant to this table, or 3 by 3 table of symbols, which you can multiply and add to each other, as is the case here. And specifically, the formula, in this case, more concretely, the formula is the following. There's a simple rule how to calculate it. And the rule is that you have to go along the first row. So you have I, and then you have j, and then you have k. So the formula will have 3 terms, one corresponding to I, one corresponding to j, and one corresponding to k. The term corresponding to I is obtained as follows. You simply cross the colon and the row where you have I. So what remains is this 2 by 2 square. And in this 2 by 2 square, you take the product along this diagonal minus the product along this diagonal. So this minus this. In other words, what you have is I multiplied by y1, z2 minus z1, y2. This is the first term. For the second term, we take j, and to get the corresponding term, we cross out the row and the colon where j is positioned. So what you end up with, again, is a 2 by 2 square. You kind of put them next to each other. So you get x1, z1, x2, and z2. And you take this diagonal product minus this diagonal product. So the result is j times x1, z2 minus z1, x2. And finally, you do the same to k. So the result is this square. Then you get x1, y2 minus y1, x2. And there is one more thing you have to remember. You have to remember to alternate the signs. So you put plus here, minus here, and plus here. Well, this you don't have to put because it's the first term. So I put equal, meaning that I'm continuing that formula. OK? So very explicit, something you have to play with it to memorize. Not too difficult. Yes? What about? Yeah, you can use, the question is, what about some other rule, which I couldn't hear? But you can use whatever rule you like, as long as you get the right answer. It's fine. I'm sure some people can just look at it and tell you the answer. I think it's much easier than doing the Rubik's Cube, to be honest. Some people can do it in like 20 seconds. So, not me. All right. So I'm sure each of you will have their own way to calculate this. I just told you mine, which, well, it's not mine, of course, but the one I use, and which I think most people use. OK. So that's a cross product. And so again, you have two different definitions. One is geometric. It's about the vectors and their positions and the angle between them and the lengths and so on, geometric characteristics. And the second one is algebraic in terms of just the components of these vectors. And so what it means is that you can also apply this to calculate various things. For example, you can calculate this way the area of the parallelogram, which is spanned by these two vectors, because the area of the parallelogram is just the magnitude of this vector, right? So we can use it to compute the area of the parallelogram. By simply taking the magnitude of this vector, which is to say, taking the square of this coordinate plus the square of this coordinate plus the square of this coordinate and taking the square root of the result. Let's do some Let's do some calculation. Let's say example, find area of the parallelogram. Let me just, to save time, write parallelogram like this. Spanned by the vectors A, which is equal to 1, 2, 3, and B, which is equal to -2, 3, and 1. Okay? Just random numbers. Okay, very easy. So first of all, we calculate the cross product between these two vectors by using this formula. So we put I, J, K, 1, 2, 3, -2, 3, 1. It would be embarrassing if the answer is 0. Okay, kind of. So they would actually be parallel. Although that would be a good illustration of that case. So, so I is equal to, in front of I, we have this one. So it's 2 minus 9, right? And then you have to put minus. Remember, there is a minus. Maybe I should emphasize it. There is a minus here in the middle. So I put a minus. And then you have J, so you have 1 plus 6. Okay? And finally, you have, in front of K, you have this, 3 plus 4. So that's -7, -7I, minus 7J, plus 7K. Okay? So that's the cross product. And you want to calculate the area. To calculate the area, I have to take the magnitude of this vector. Please check my calculations, because who knows. So now the magnitude is just the square root of the sum of the squares, which is 7 squared plus 7 squared plus 7 squared, which is 3 times 7 squared, which is 7 times square root of 3. So that's the final answer. Any questions? Okay. So that's the cross product. And yes? That gives us the area of that parallelogram. I'm sorry? Does it look like distance formula? Well, it looks like distance formula for a reason, because what we're calculating is the length of this vector. And the length of the vector is given by the same formula as the distance formula for the distance between the initial point and the end point, right? So in this case, the initial point is 0, 0, 0, and the end point is -7, -7, 7. So that's why we simply have to apply the distance formula. We are applying the distance formula, right? So let me just say this, since the question was asked. If this is a vector, and just any vector, not necessarily coming from this problem, could be from any problem. If I have a vector, the length of this vector is just the distance between the initial point and the end point. So if this is point A and this is point B, it will be the distance between A and B. And so it would be equal to the square root of the squares of the distances, of the differences in coordinates. All right. In the case of a dot product, there was a special case when the cosine was 0. And cosine is 0 when two vectors are perpendicular. In the case of cross product, there is also a special case when sine is 0. But unlike the cosine, sine is equal to 0 if theta is equal to 0 or pi. Which is to say that the two vectors either point in the same direction so that the angle between them is 0, right? Or they point in opposite directions. Right? So in this case, the cross product, according to the first formula, is the 0 vector. Right? Because the first formula tells us that you get a vector whose magnitude is 0. There is only one vector whose magnitude is 0, and that's the 0 vector. And for a good reason, because in this case, if the two vectors A and B are parallel to each other, there is no plane which they span. So we cannot speak of a plane, we cannot speak of a vector perpendicular to this plane. Therefore, the only answer that we could possibly get is the answer 0. Which incidentally is a very good opportunity to talk about the vector 0. Because this is something which people might find confusing. Partly the confusion is due to a very unfortunate choice of notation that we have. So I'd like to say it once and for all, kind of to explain this once and for all. There are three different objects which are denoted in almost the same way. You have to know the difference between them. One is 0. One is 0 like this. And there is also O. So how do you distinguish between this? So I'll kind of, just to emphasize, these are numbers, 0, and this is O. OK? So what are these objects? This is the simplest one. This is just number 0. This is something which you don't need to take. To understand this, you don't need to take multivariable calculus. You don't need to take calculus at all. Right? It's something which we all know what 0 means, hopefully. Now, this is something which is very much to the point here. Amongst all the vectors, we have vector 0. And the easiest way to explain what vector 0 is to think about vectors the way I explained last time. To think about vectors as a shift. To think of a vector as a shift in a three-dimensional space, as an operation of a parallel transport of all points in space. Applied to each point, it gives you another point, which we illustrate, in general, we illustrate by a vector, by an arrow like this. Right? So this vector is equal to this vector, to this vector, and so on, because we shift the entire blackboard this way. So each point gets shifted in the same direction with the same magnitude. But once we start talking about shifts, we have to include a very particular shift, namely a shift by nothing, the identical transformation. We do nothing. If we're allowed to take any shifts whatsoever, we certainly should be allowed to take a trivial shift, a shift by 0. That's the vector which is represented in this way. Now, we can't really draw it because, see, we usually draw it because to draw it, we use the initial point and the final point, and then we connect them by a segment, and then we place an arrow to indicate from where to where we are going. If there is no shift, we start and end at the same point, and then there is no place to put an arrow. So it starts looking like a point, which it is not, okay? Because as we discussed, that the point is just a static object in space, which is doesn't know about anything else, just about itself, right? And a vector is a totally different concept. A vector is not a point. Vector rather is an operation which you apply to all points at the same time. And that's why we can represent each vector by an arrow starting at each point. So this is a special vector which corresponds to the transformation by nothing, okay? That's what it is. Now you can ask, why do we need it? Why do we need such a transformation? If it's nothing, it's not going to help us. It is important because we have to include it for consistency. Because we know that vectors, we want to have various operations on vectors. For example, addition of vectors, multiplication by scalar. So for instance, we can take two vectors which are pointing in the opposite directions and which have the same length. Such vectors we can call A and negative A. Negative A simply means that it has the same magnitude but points in the opposite direction. Now, we would like to have a consistent system of vectors in the sense that if we take the sum of two vectors, we are going to get another vector. So in particular, we should be able to take the sum of these two vectors. What's the answer? We have to have a vector which is the sum of them, but the sum of them is precisely this transformation which I'm talking about. You first shift the blackboard this way, but then somebody comes and says, no, 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 put it back. So you shift it back. The net result is that you did nothing. But sort of nothing came out as a result of something. So to be able to have a sum of these two vectors, we have to have this vector on our books. That's why this vector is important. It's one of the reasons. We would not have a consistent system of vectors if we did not include this. But note that this is not the number 0, because the sum of two vectors is not a number. In fact, if we want to represent it in coordinates, we would have to write it like this. And again, I emphasize that these are not letters, but numbers 0. So that's the difference. This is just 1 0, and these are 3 zeros, right? So it's different. But of course, these 3 zeros, the meaning of these 3 zeros is very special, because for a general vector, like vector A, this 1, 2, 3 would correspond to the components of this vector. Here, this is a vector which has component 0 in each place. Okay? So I hope that the difference between these two is clear. And finally, we also have this, as if this was not enough. We have one more object which almost looks the same, or notation for which looks almost the same. And that is actually the point, which is the origin. When we draw our coordinate system, we oftentimes, so it's like this, right? So it's x, y, z. We oftentimes need some notation for this special point, because there's this very special point in the three-dimensional space once we introduce the coordinate system, which is at the center of the coordinate system. We call it the origin of the coordinate system. So we oftentimes need a letter for it. And because it's called origin, it's natural to call it by the letter O, which is very unfortunate because it looks like 0. No? Right? But it's not 0. The point is, however, that you can represent, so this is the letter O, but you can write, just like every point P, you can write it in coordinates. And the coordinates would be 0, 0, 0. You see? So now it looks very much like this, but not the same, because if we use the round brackets, we are talking about points. And if we use the angle brackets, we are talking about vectors. So this corresponds to the actual point, right? The actual point, which just sits here and it doesn't know anything about other points. Whereas this represents a vector which you can think of as a transformation of the entire space, which you can apply to any point. It's just that the result will be that same point. You can apply it to this point, but you can also apply it to this point. And that's what the difference between these two we indicate by different notation. So this is something to chew on, I guess. If you're still confused about this, just think about it. I think it's fairly self-explanatory, but I think you will not be able to make much progress in this area which we are discussing now if you don't clearly understand the distinction between these three objects. So this is a very good test, how well you understand vector analysis and coordinate system in three-dimensional space. And I really wanted to emphasize this because this is one of the most common points of confusion. All right. Are there any questions about this? OK. So what do we do next? Next, actually, we are ready to do some fun stuff in space. We have basically laid the groundwork for it. We have developed the formalism we need, by which I mean finding vectors, defining vectors, and studying some of their properties. And now we can actually use this formalism to start representing various geometric objects in space. So what kind of objects am I talking about? Sorry? Say again? Conics. Conics we will also represent, but there are simpler ones. So we will start with the simplest ones, and we will progress to the harder ones, right? So which seems like a good strategy. Conics will be sort of the next level of difficulty. That's right, lines and planes. This is something I already told you about earlier. The simplest objects are linear objects, which means in dimension 1, lines, and in dimension 2, planes. It's sort of I guess it's sort of a philosophical question as to why these really are simplest objects. But mathematically, it's quite clear, because the equations and formulas which you use to represent them are the simplest possible ones, as you will see. So when we try to build the formalism for representing general curves and general surfaces in three-dimensional space, it's natural to start with lines as the simplest curves and planes as the simplest surfaces. So let's start with lines, and let's talk about ways of representing lines in three-dimensional space. And here, the idea that will be very useful is the idea which we learned when we studied parametric curves on the plane. The idea we learned back then is that to understand the general curve, it is a good way to understand the general curve is to parameterize it by an auxiliary parameter. So here, you have a line. And by this, I mean a general line, not necessarily in this blackboard, but could be on one of those tilted blackboards. So you have somewhere in the background the three-dimensional coordinate system, which you are going to use to represent this line. So we have to decide how best to parameterize it. So the first point is that what information do we need to describe this line? And here is one convenient way to describe it. To determine a line, I have to tell you a particular point on that line, and I have to tell you a direction of this line. Right? And directions we have now learned to describe in terms of vectors. So what I'm saying is that in order to describe a line, it is sufficient to pick a point let's call it L. Pick a point of L. And second, pick a direction vector. we are going to call this vector v. And let's call this point P. Now, neither of these objects is unique. I could have chosen this point or this point or this point, anything from the infinitely many points which belong to this line. Likewise, the direction vector is not unique either. I could take any multiple of this vector. I could take this vector, or going in the opposite direction, like a vector, for example, this one would work also. So this is not unique, but I have to make some choices. And once I make these choices, we will have determined completely what the line is. So all we need to do now is to give a description, a parameterization of other points on this line. We already have one of them, so we need to find other points. And doing this is actually very simple, because we can now take advantage of the notion of addition of vectors. So here, let me explain this. Let me draw the position vector of this point. I recall that the position vector of a point is a vector which has the origin, the letter O, as the initial point, and our point P as the final point. So that is the position vector of this point. So now I would like to find other points on this line. And finding other points is the same as finding position vectors of those other points. So for example, I know another point on this line, which is this point, the end point of this vector. So the question is, how do I find the position vector of this point? Well, for this, we can use addition of vectors. And I recall that if you have two vectors, you can use the triangle rule to find the sum between them. Here, they're perfectly arranged for that. I first move from the origin to this point, and then I move from this point to this point. So what's the net result? The net result is I move from the origin to this point. So let's call this position vector by R0. And let's call this vector R1. Then what I'm saying is that R1 is equal to R0 plus V. So now, by using addition of vectors, I have been able to find a different point on the same line. What about the rest of the line? Well, to get to other points, I can argue as follows. If I take any other point, say this one, the vector which connects my initial point P to this one, let's call it P prime, can be expressed as a multiple of the vector V. Right? Because parallel vectors are all proportional to each other. Certainly the vector P prime, P prime is proportional to V. So there is some number T0, T1, say, for which we'll have this formula. For some number. Actually, this simply means the product of V and the scalar T. We can write it like this, or we can write it in the reverse order, T1 times V, it doesn't matter. For some number T1. Right? But if so, then I can find the vector P prime, OP prime, as R0 plus V times T1. To see it on the diagram, simply take this vector. You find the position vector for this point by taking the sum of the initial one and this one, which is v times t1. Right? But in fact, this is true for any point p prime. So for each point p prime, there will be a particular number t1. Or maybe it's better to just call it t so that we don't worry about the indices, right? And so we see that this way we can actually parameterize all points on this line. So in other words, we can write the position vector, say r, for a general point on this line as r0 plus vt. And that's going to be the crucial formula. So you see, we have exploited the notion of addition of vectors. This is why it was important to talk about vectors and about addition of these vectors, because otherwise it wouldn't be so clear how to get to those other points which belong to the same line. Now, let's write this formula in components. Let's write it in components. So we'll say R is x, y, z, and R0 is x0, y0, and z0, and v is a, b, c. These are three vectors. So now we just write this formula out in components. So we get the following. For the first one, we get x is equal to x0 plus at. For the second one, we get this. For the third one, we get this. And now we look at this, and we recognize that it looks very similar to parametric representation of curves on the plane, which we have talked about for 2 weeks or a week and a half, right? And for a very good reason, because in fact this is a parametric representation of the line L. Right? Because I have now parameterized general points of this line in terms of some auxiliary coordinate t. So it certainly is very reminiscent of the general formula for a parametric curve on the plane. The difference is that when we talk about curves on the plane, we only have two coordinates to describe, x and y. That's why there are only 2 lines instead of 3 lines here. Now we work in the 3-dimensional space, so we have to specify the dependence of each of the 3 coordinates. But otherwise, it looks very similar because this is some function. You can call it f of t if you want. This is another function called g of t, and this is a third function which we can call h of t. Are there any questions about this? So I explained to you how to derive it by using vectors. But once you have the end result, you recognize that this is simply a parametric representation of the line. So in practice on homework and on various tests, you're going to be asked to find parametric representation for a line like this. And this is really easy because all you need to know is a particular point on this line and a particular vector on this line, or particular vector which goes along this line, like this vector v on this picture. That's all you need to know. And you can use the data which you are given in a given problem to find a point and the vector. And then you just combine this information in a formula like this. So here is an example. It's a very typical question. Find the line which passes through the points 3, 1, negative 1, and 3, 2, negative 6. So that's another way to describe a line, because a line is also determined if you specify 2 points on it, right? There is a unique line which passes through 2 different points. The points should be different. Otherwise, if 2 points coincide, there are many lines which pass through 1 point. But if points are different, then there's going to be a unique line which passes through it. So, but we would like to convert this information into the information that we need for this parametric representation. And so we need to know a point and the direction vector. So the point will represent by this position vector r0, and the direction vector will be our v. In this case, we actually have 2 points. So you can choose either one. It's your choice. So pick one. Let's say the first one, 3, 1, negative 1. So your r0 is, so you see I'm being really rigorous and pedantic here. I'm distinguishing between the point and the position vector of this point by using different brackets. The round brackets for points, the angle brackets for vectors. It's very important, as I already explained. So this is your x0, y0, and z0. And now, to find v, we can simply take the difference between the position vectors of these 2 points. Right? If you have 2 points on the line, you can surely find this vector by taking the difference between this vector and this vector. So this is v. You can write v as OP prime minus OP. So I simply take the difference from 3 to negative 6. I subtract 3, 1, negative 1. What's the result? The result is 0, 1, and negative 5. So now I have found what I needed, which is I have found a point on this curve, on this line, and I have found the direction vector. And now I just put all this data into this formula. Right. So the end result is x is equal to, these are my x0, y0, and z0. So x is 3 plus, this is v, plus 0 times t, which I can just erase, just write like this. Y is equal to 1 plus 1 times t. Z is equal to negative 1 minus 5t. So that's the answer. When I say it's not the answer, it's one possible answer, because someone else could instead choose as a reference point not the first one but the second one, or take the vector v, the difference not from this to this but from this to this, or even a multiple of that. So in other words, you have to realize that there is not a unique parametric representation for a line. There are many different ways. So if you get a different answer from your friend, it doesn't mean that one of you made a mistake. It could be that both of you have the right answer. Any questions about this? Now, there is another way to to write an equation of a line. In general, we're going to have this formula, right? So let's focus on this formula. Suppose that A, B, and C are all non-zero. Then we can express t from each of these formulas by dividing by A, B, and C. So we can find that t is equal to x minus x0 over A. T is y minus y0 over B. And t is also z minus z0 over C. But it's all the same t. So we could write the following formulas: x minus x0 divided by A is equal to y minus y0 divided by B equals z minus z0 divided by C. So that's another way to represent a line. This is the first way. And this is the second way. I would like to explain what happens if one of these numbers, a, b, c, is actually equal to 0, which is the case we have in this particular problem. So if a is equal to 0, then we have the equation x equals x0 instead of x equals x0 plus at. Right? So in this case, we cannot express t from the first equation because t is not in this equation. But we can express t still from the second and third equations provided b and c are non-zero. So if a is 0 but b and c are non-zero, we can write x equals x0 and y minus y0 over b equals z minus z0 over c. So we get two equations like this. It's not surprising that we get two equations. In fact, here it looks like one equation, but that's because of sort of a nice way in which I wrote it. It's not really one equation. There are two equality signs. This line actually represents two equations. This is equal to this, and also this is equal to this. These are two separate equations. And someone can say, wait a minute, it's actually three different equations because it says this is equal to this is equal to this, and also this is equal to this. But the third equation follows from the first two because if this is equal to this and this is equal to this, then the first and the third are equal. That's the usual kind of logical implication that we have for the equality. So this really corresponds to two equations. Two equations. And we can see it more clearly in the case when a is equal to 0. There are indeed two equations in this case. So in both cases, in the general case when a, b, and c are all non-zero, or in the special case when a is equal to 0 but b and c are non-zero, we have two equations describing a line. There is also a special case when both a and b are equal to 0, but c is not equal to 0. I'm not going to tell you what the answer is. You'll have to figure it out on your own. But you will see that it's also two equations. And a and b and c cannot all be equal to 0 because that would mean that this vector v is equal to 0. But I insisted that this is a non-zero vector. Pick a direction vector. I have to make this say non-zero. For otherwise, we wouldn't be able to do this, to argue in this way. What's your question?
I didn't have a question.
Are you explaining? Oh, great. But sorry? If a is equal to 0, b is equal to 0, and c equals equal to 0, then v is not defined. Well, v is defined, but v cannot be used in this case. V has to be a non-zero vector. Now, so you see what happened is that we found actually two different ways to represent the line. This is the first way. And an important feature of this first way is that we have one auxiliary parameter which we use to parameterize it. One parameter. Or we can write it in this way, which really means that we write two equations for this line. And now I want to remind you that when we talked about curves on the plane, I explained that there are two different ways to represent a curve. This is the first way, when we have one parameter. But then there is also a second way in which you have one equation. Like y equals f of x. Maybe let's call it f capital to not distinguish with that. Or the favorite equation for the circle, x squared plus y squared equals 1. So remember, there was exactly the same picture in the case of curves on the plane. We learned two different ways to represent such a curve. One is a parametric way, where we use one parameter, and another one is by means of an equation. And then we have one equation. So what I want to emphasize now is the dimension count. Here we talk about curves, which means dimension 1. Curves in the plane. The dimension of a curve, is 1. And the dimension of the ambient space is 2 in this case. Because we talk about curves, this is about curves on the plane. I'm not going to write it down. I'm talking, yes, I did. Curve on the plane. So the object itself has dimension 1. And its ambience, it's immersed, it's put in an ambient space, which has dimension 2. So when you parameterize it, the number of parameters is going to be equal to the dimension of your object. In this case, the dimension is 1, so there is one parameter. But the dimension of your object, as I explained earlier, is equal also to the dimension of the ambient space, minus the number of equations. In this case, we have dimension 1, which is equal to 2, which is number of variables x and y, the dimension of the ambient space, the plane. So we have to subtract 1 to get down from 2 to 1. That means that the number of equations for a curve on the plane has to be 1. That's why a circle is given by one equation, x squared plus y squared equals 1. That's why graph of a curve is given by one equation, y equals f of x. What happens now is that instead of working on the plane, we work in space. And in space, the dimension is 3 and not 2. So the dimension of the ambient space now becomes 3. But we are still talking about curves. Well, more specifically, we are talking about lines. But lines are special examples of curves. So our object is a curve. But now, so the dimension of the curve is still 1, but the dimension of the ambient space is 3. If you want to parameterize it, you have to still use one parameter, just like for curves on the plane. That's why it's not surprising that we end up with a parametric representation with one parameter. But if you want to describe your line by equations, you have to use two equations now. Because you have to be able to come down from 3 to 1. You have to drop the dimension from 3 to 1, so you have to impose two independent equations. Right? So 1 is equal to 3 minus 2. That's the number of equations. That's why it's not surprising that we really have two equations describing this line. Well, in this case, I arranged them neatly in sort of one equation, but as I just explained to you, it's not one equation, but it's two equations. Or in that case, also clearly two equations. So the same principle that I was talking about earlier of dimension count, dimension of an object being the dimension of the ambient space minus the number of equations, still works here. And it will be interesting to see now how it works for planes. Before I get to planes, I just want to mention one thing, which is that you can be asked various questions about lines. Once you learn how to represent them, you can be asked about relative positions of lines. And what can happen with lines is that lines can intersect or not. That's one possible question. Do these two lines intersect or not? Another question is, are they parallel or not? And so, in fact, there are different relative positions that can happen. First of all, two lines can just intersect. Right? So that's a possibility. And you can easily find out whether it is the case. You simply write the equation for the first line with using parameter t, and then you write the equation for the second line using a different parameter s, because these are two different lines. A priori, they don't talk to each other. So they have two different parameters. So what you need to know is whether for a special value, let's say this one is parameterized by parameter t, but this one is parameterized by parameter s. So you want to know whether for some t equals some special value t0, there exists some special value s, which is equal to s0, so that the resulting point is the same. And if you write this down, you will get a system of equations which may or may not have solutions. And that's how you know whether they intersect or not. The second issue which arises here is whether these two lines are parallel to each other or not. And that's real easy, because part of a parameterization of the line is a choice of a direction vector. Two lines are parallel if and only if the direction vectors are proportional. How do you know if they are proportional? Well, you just see if one of them can be obtained by multiplying the other one by a scalar. That scalar will be immediately determined by the first coordinates. And then you check whether it works for the second and third coordinates. And that's how you see if they're parallel or not. So questions like this. But once you have this parameterization, you can handle them. Finally, it's possible that the lines do not intersect and are not parallel to each other. It's also possible. And here is an example. So let me keep this one, this line. So let's suppose I have this line. If I have also this line, first of all, this line can intersect this one easily, even if it's not in this plane. It could be in another plane. It could be a more general line, right? It can also be parallel, right? But these are not the only two choices, because it can be parallel to this plane, but not parallel to the line. So it can be like this. So if you kind of look like in this way, you see that they kind of intersect. But actually, in 3 space, they don't intersect because there's some distance between this line and this plane. So in this case, they are called skew. And again, it's very easy to find out whether they are skew or not by using parameterization. OK. So in the remaining minutes, I would like to talk about planes. So I talked extensively about lines, but now I want to talk about planes, which means that now these are objects of a different kind, right? Because now these are objects which are two-dimensional. In the case of curves, we had analogous objects on the plane, because the plane was two-dimensional, so the plane fits one-dimensional objects, curves, in a nice way. But the plane cannot fit any two-dimensional objects except itself, right? Or maybe you can cut some piece of a plane. It's also two-dimensional, because it is already two-dimensional itself. But in 3 space, we can now have all kinds of surfaces. And again, the simplest surfaces which we study are the kind of linear surfaces, the planes. The question is, what is the best way to represent a plane in a 3-dimensional space? So we look again at these two options. One is to parameterize. The other one is to write equations. If we were to parameterize a plane, we would need two parameters, not just one, because it's two-dimensional. But if we were to write down equations, we only need one equation, right? Because for a plane, the dimension of a plane is 2, which is 3 minus 1. So that's the number of equations. So we need to find a nice way to write an equation. Clearly, it is more economical to represent a plane by an equation than to try to represent it in a parametric form. Because in parametric form, we would need 2 parameters. Formulas would be rather complicated. But we only need 1 equation. So let's just find out. Let's find a good way to write down equations for these planes. And the point is that there is a very nice way to get to this equation, because a plane can also be determined by a vector and a point. So remember, we discussed that a line can be determined by a point on this line and a direction vector. In the case of a plane, there is no direction vector. If there were, it would be a curve. It would be one-dimensional. So instead of talking about a direction vector of a plane, it is much wiser to talk about perpendicular vector to a plane. So a plane, unlike a curve, is determined by a point on the plane and a vector which is perpendicular to it. So instead of vector v, which is sort of like direction vector in the case of lines, we are going to have a perpendicular vector determined by, and I will just draw it as a picture, by a point P and a vector n. Point, vector n, perpendicular to the plane. So now, how do we write down an equation? Here we use the cross product. So that's where the cross product really comes into play. Because if you have a different point P prime, and you connect these 2 points, this vector n is going to be perpendicular to this vector. You can easily see it on that, using that board. You just say. So this is your vector from P to P prime. This is your plane. This vector is perpendicular to any vector that you can have inside this plane. But the condition of being perpendicular can be expressed by using the dot product. I'm sorry, I said cross product. I meant the dot product. So I'll just write down this equation. So the equation is that n dot p prime, dot p prime is equal to 0. This is a dot product. Because remember, we discussed and we agreed that 2 vectors are perpendicular if and only if the dot product between them is 0. That's what I'm writing. Now, if I write n as a, b, c, and I write pp prime as before as x minus x0, y minus y0, and z minus z0, and use the rule of dot product, I will find the following equation. So here you have one equation in which a, b, c, x0, y0, and z0 are given, and x, y, z are the free variables, right? And all x, y, z which satisfy this equation correspond to the totality of all points on this plane. So as promised, a plane is given by one equation, and here's a way to derive this equation. Okay? So once you have this equation, there are all kinds of questions that can be asked. For example, if you have 2 planes, are they parallel to each other or not? What is the angle between these planes? But all of this can be immediately learned from this equation by looking at it and interpreting the coefficients a, b, c, and x0, y0, and z0 as this data. Okay? So I stop here, and I want to say one thing, which is that I have posted the solutions for the homework, for the first homework set, on the B space. And I will be posting them regularly every Tuesday night when the last of the sections, just when the last of the sections is over. Okay? So I'll see you next Tuesday. But the output is a number. The output is a number. And I explained last time that there are two ways to define the dot product of two vectors. The first way is geometric. We talk about the magnitudes of the two vectors and the cosine of the angle between them. Which we call theta. So it's just the product of these three numbers. But there is also a second way, which is very convenient in calculations, which is defined in terms of the components of the vectors. And those components will be called x, y, and z. So I put index 1 for the first three components and index 2 for the components of the second vector. So the formula looks like this. Now, we can play with these formulas, and we can derive useful information about vectors by using the fact that both formulas give us the same answer. Okay? For example, we can find the angle theta, the angle between the two vectors, by combining these two formulas. From the first formula, we learn that the cosine of this angle is equal to the dot product divided by the magnitudes. And now we use the second formula. So this is the first formula. And now we use the second one to write this in the second form, xy, x1, x2 plus y1, y2 plus z1, z2, divided by the lengths. But the lengths can also be found from the components. For example, the length of the first one is given by this expression. And likewise for the length of the second expression. So we can write this also very explicitly using the components, or coordinates, if you will. So you see, this is an unexpected formula in the following sense. You have two vectors, and which are given by these coordinates x1, x2, x1, y1, z1, and x2, y2, z2. When we just look at these coordinates, we don't know where exactly the vectors are. We'd have to plot them in space to really understand their relative position. So it looks like it would be very difficult to find out what the angle is between them. But in fact, there is a very explicit formula which uses nothing but the expression for A and B in terms of components. Right? So this formula only uses x1, y1, z1, which are the components of A, and x2, y2, and z2, which are the components of B. And a priori, there's no reason to believe that there would be such a formula. But we were able to derive it by combining two different definitions of the dot product. It's not like it's very simple, but it's not too complicated either. I mean, it involves some square roots and so on, but it is very explicit. So, for example, you can program it on your computer, and then every time so your program on the computer would be like that black box, the dot product, for example. So you can program your computer to calculate the dot product, you get a number. But you can also program your computer to calculate the cosine of the angle by simply calculating this. And that's very simple, which can be done very quickly. So that's the power of these methods that we are talking about. That using these methods, we can learn a lot about the geometry of vectors, say, or other geometric objects, by using as input algebraic information, such as the components of these vectors with respect to the x, y, z coordinate system. One application of this is the following. There is a very special angle for which, special angle theta, for which the cosine is equal to 0. So cosine theta is equal to 0 if theta is equal to pi over 2. Or actually, not just one, but two different values, pi over 2 and negative pi over 2. Right? Right, so if you have an angle like this or like this, the projection onto the x-plane, which is the cosine, is equal to 0. So in this case, the dot product formula tells us that the dot product is 0 in this case. So we can use it, you can use this formula to determine whether the vectors A and B are perpendicular to each other or not. When I say perpendicular, I mean that the angle between them is 90 degrees. But to say that the angle between them is 90 degrees, well, it means that they are either like this or like this. Right? It doesn't matter. In both cases, they are perpendicular. And in this case, A dot B is equal to 0. So if you are given two vectors, it's very easy to find out if they are perpendicular or not. You simply take the dot product given by this very simple formula, number 2, and you see whether if it's 0, they are perpendicular. If it's non-zero, they are not. So that's a useful application of all this formalism. There is one more operation that we will need for vectors, and that's called the cross product. Now, the terminology here is really not very, doesn't really make much, how should I say? It's not very imaginative in some ways. It's just that in the first case, we denote it by a dot, so we call it dot product. In the second case, we use it denoted by a cross, so it's called cross product. There is no underlying reason for calling them this way. It's just a tradition. So don't try to read too much into this terminology. It's just the way it is, because of the kind of notation that historians. Hi. So what are we doing here? We are studying vectors in three-dimensional space, right? So last time we talked about what vectors are and what we can do with them. So what can we do with vectors? We can take the sum of two vectors. We get another vector. It is on. Let's see. Let me see if I can adjust it. Is that better? No? What is it about microphones in this class? By the way, I did find batteries after I finished my last lecture. They were hidden in the cabinet. So don't make me do this. Because you don't want that. Let's see. Like this? Better? Yes. Okay. But tell me if you lose me. If I lose battery. So. All right. Yes, we can take the sum of two vectors, and that's a vector. Or we can multiply a vector by a number. That's a vector. But in addition, there are also more sophisticated operations we can do on vectors. For example, dot product. Now, a dot product is a whole different deal because the input of a dot product is two different vectors.